Hello everyone, welcome to a fresh new lecture on the applications of fast Fourier transform. So, this is a part of the course Signal Processing Algorithms and Architectures. I am Dr. Anirban Dasgupta and let us get started. Okay, so here we are trying to understand three applications of FFT. Now, applications I mean to say that not only how we can use this FFT or the spectra for some practical use, but also how FFT is reducing the complexity. Okay? So, first is filtering long sequences, second is frequency estimation, and the third is the power spectral density estimation. So, filtering long sequences, what does it mean? Now, when I am speaking, probably there can be some noise, maybe the AC is making some noise and I want to filter that. And we already discussed that when we want to filter such sequences, we can simply use a linear filter which does convolution. Now, what is the problem? So, suppose my signal is of length Lx and my filter is of length Lh. Now, if this signal is of length Lx which is long, my number of multiplications will be pretty large. So, what is the problem? Let us not consider additions as of now, because multiplications are the more time taking operation. So, the sequence if it is long, then it will be computationally expensive. So, can we do better? So, what we will do is we will use the FFT. How? So, we will break the signal into small sub signals and then we will do filtering in the frequency domain. So, what advantage do I get by filtering in the frequency domain? So, convolution in time becomes multiplication in frequency, that is one thing. And second thing is that the conversion from time to frequency can be done in faster way using the FFT. So, the two popular method of achieving this is called the overlap save method and the overlap add method, and these two are collectively called sectional convolution, because we are dividing the signal into sections and then performing the convolutions. Okay. So, what are we doing? The first method is overlap save method. So, in this we will first divide the signal into overlapping sub signals or overlapping blocks, as the terminology says, and then what we will do is we will filter each subsequence. Now, there is a rule for doing the overlap. So, first let the input sequence be of length Lx. How this Lx is formed, we will take an illustration. So, this is the whole signal Lx, okay, and we have the filter length m, fine, fair enough. So, now we will break the input signal into overlapping segments, and how we will be overlap? So, say this is the signal which is starting from this point. So, what are there before this? Since this is a signal, technically this is the span of the signal or the support of the signal, but beyond this the signal has 0 values. So, if I define a signal x of n and which is 0 to Lx minus 1, then beyond this index 0 the signal values are 0, and beyond the index Lx the signal values are 0. So, the logic is I will take m minus values from the previous block, and in this case there are no previous blocks, or the previous values of the signals are 0. So, for the first sub signal x1 n we will pad m minus zeros to the front. For the second sub signal x2 n we will take m minus 1 values from the last m minus values of this block or x1 n. Similarly, for the third sub signal x3 n we will take m minus values from the previous block x2 n. So, this is from the input side. What about the output side? Now, in the output side, since these are formed because of circular convolution, so these first m minus 1 blocks are technically redundant. So, we can discard this, discard this, discard this, and then just concatenate the signal which is my final yn. That is it. But it might sound complex. So, let us take an example. So, let us say this is my sequence, and what is the length of the sequence? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, my Lx is 10, m is 3, this is the length of the signal. Now, practically you will not get a length of 10 and you have to do sectional convolution, because this you can do directly, and that is why I have taken a length of 10, because I can show you that the result of direct linear convolution is same as the result of overlap save method. But in practice you may get 10,000 or even 1 lakh point signals, which is huge. So, what will I do? Now, I will form the subsequences. So, first subsequence, so what should be the subsequence length, which is my L. Now, how many point FFT or circular convolution I want to perform, that is very important. So, here let us decide that I want to perform 8 point circular convolution, and my m is 3, which is the filter length. So, what will be L? L will be n minus m plus 1, which is 6. What does it mean? We will take 6 values from the signal and then m minus 1, m minus 1 is 2. So, 2 zeros, 2 zeros or 2 values from the previous block and 6 values from the signal. This is my x1 n. What about x2 n? I will take 2 values, these 2 values, sorry, this is not the signal, this is the signal. So, let me erase this for confusion. So, this is my signal. So, I take the 6 values from the signal. Similarly, these 2 values, the first 2 m minus 1 values will come from the last m minus 1 from the previous block, which is 3 and 2, and the remaining will be these values 0, 1, 2, 1, and since I am out of signal, so what is there after 1? There are zeros up to infinity. So, I take zeros as many to make it 8 or n. Now, I will do circular convolution. Now, in the time domain I am doing this circular convolution because this is just an 8 point sequence, but practically I want you to know that the circular convolution will be done as a multiplication in frequency domain, and this conversion to frequency domain will be performed using FFT and IFFT, which will take n log n complexity. So, these two will be your result. So, again I see this is my y1 n and this is my y2 n. Now, I have to do something called overlap and save to find the final subsequence. So, this is my first subsequence, which I say y is y1, and this is my second subsequence, which is y2. Now, what to do next? As I said, I will discard m minus 1 values of y1 and y2, which means I will discard these 2 and save the remaining. I will discard these 2 and save the remaining, and then if I concatenate, I get this signal, and just check this is exactly same as the signal output which I got by direct linear convolution. So, overlap and save works for this specific example, and you check out any problem, this will work. What about the next method, overlap add? So, here what we are doing, we are not overlapping anything from the input side. So, we will just take L blocks, L size blocks as x1, x2, x3, but with L I cannot perform n point circular convolution or n point DFT. So, I have to pad m minus 1 zeros at the end. Now, as I pad these m minus 1 zeros at the end, now my subsignal length becomes of size capital N. So, now when I do the convolution, circular convolution say, so I will get these output blocks. Now, what will I do is, I will just overlap these m minus 1 points, and as the name suggests, it is overlap add, I will directly add them. Again, if it is confusing, let us take an example. Let us take the very same example. So, this is my signal and this is the result of linear convolution, and we have all this chalked out easily. But here what we are doing is, so we are taking 6. So, 6, 1, 2, 3, 4, 5, 6, and the remaining will be this. Of course, these two are, since there are zeros after this, so I have taken 0, 0, and these m minus 1 zeros are padded at the end. And now do the maths, now do the circular convolution, you get these two signals or subsignals as outputs. And as I explained, so you have to overlap these m minus 1 of the last and m minus 1 of the first. If there were more signals, so you have to again overlap the y2 and y3. I try to keep this as a simple exercise, and then so these are directly coming, only these two portions will be added. So, 5 plus 0 is 5, 2 plus 1 is 3, and you check the result, this is your yn, which is verified. So, overlap add also works. And just a summary of comparison. So, here you have overlapping input segments in overlap save. In overlap add you have non-overlapping input side, but the output side you need to overlap and add. So, here you are overlapping m minus 1 samples between the blocks, and here the m minus 1 samples are overlapped at the output. Overlapped in this case means you are taking from the previous block, and here you are discarding the m minus 1 samples because these are coming from time domain aliasing, and here there is no need of discarding, you are just keeping them but adding, and this is direct concatenation, and this is overlapping and then adding to get the result. So, these are the 4 main differences. With more practice you will get things easier. So, let us move on to the second example, which is frequency estimation. So, what is the problem of frequency estimation? Now, this is the analog case where I represent xt as composed of some sine waves which are varying at different frequencies, having different phases and different amplitudes. Well, this looks just like the Fourier series, the continuous time, but here we have something else, we have the noise. So, the problem is that I want to exactly find what frequencies are present in the signal, or I would say dominant frequencies, because there are something which is called SNR, signal to noise ratio. So, if the noise is very high, you may not, and if the amplitude of a specific frequency component is comparable to the noise or lower than the noise, then that signal is buried under the noise. One practical example is, suppose you are talking over the phone and then some train goes and makes a very loud noise, your signal is lost, kind of that analogy. So, what is the challenge? And this is what I was exactly talking about, that noise, and noise is very random, you cannot distinguish sometimes that which is noise, which is true signal. So, it is difficult to estimate the frequency. The second is spectral resolution. What is the spectral resolution? So, this case I said that or in the Fourier assumption is that this f1 say is your fundamental and these are all harmonics. So, if you know f1 you can just say f2 and f3 and others are just the integer multiples, but there can be two frequencies which are very close to each other. Like I worked in a project of finding say broken rotor bar fault from armature current. So, your healthy motor will have a 50 hertz component and a broken rotor can have a component which is 50.5 hertz. Now, these two components, seeing them separately is often a challenge because they are very close, and then leakage effect adds to the problem, because say if I want a 50 hertz sine, I should ideally get a peak, but in reality we do not get a 50 hertz sine, we get a sine which is of a definite window. That means multiplying that sine with a window function, and we know that because of this windowing, instead of getting a sharp peak you get a spread out peak, and probably this 50.5 will be spread out like this. So, this will sometimes appear as a single peak. and this is the same problem as closely spaced frequencies which I said. And of course, aliasing, and this is again a sampling problem. So, if you are sampling at a lower rate, anyway you get these problems. So, you have to be knowing very precisely about what frequencies you want to detect, and you should appropriately sample at that frequency. So, there are a lot of methods, and here, since this is an application of FFT, I will be discussing the FFT based method. But there are challenges like this closely spaced sinusoid problem, where there are even better methods like the autoregressive model based method. Then music is a very nice method, multiple signal classification. These are all advanced signal processing topics. Then spirit, which is estimation of signal parameters via rotational invariance techniques. So, let us see how FFT will solve this problem. And here, for our simplicity, because I like to start things with simple problems. So, here I see we have a signal x t is a sin 2 pi f naught t, and if you can always have a noise term, but for simplicity I say I do not have a noise right now, and neither I have a phase right now, but this will work with phase and the noise such that the SNR is good enough. So, now what will I do is, so of course, theoretically again this is having a span negative infinity to positive infinity, but we will consider a window maybe from 0 to some value t naught, not say t naught, I will say t, and then we are sampling this as Ts, sampling rate, sampling duration. So, this makes our discrete time equivalent sequence as A sin 2 pi f naught n by Fs. And now we will compute the DFT, or in other words we are computing the FFT, because typically this sequence length will be large. So, if the sequence length is say 10,000, we have to compute 10,000 point FFT, which is easier with FFT than DFT. Another important thing is that you can always zero pad this length to make it 2 power some v or r, whatever. So, we get the FFT. FFT means, so suppose in the continuous time spectra, considering this is of infinite duration, we should get a specific peak at f naught and possibly minus f naught. Let us say consider just the positive half, because for a real signal this will be kind of a symmetric spectra. Now, the question is, will we get this kind of a ideal thing? No, we will get some spectral leakage, as I said. So, there will be a lot of, let me use some other color if it is there. So, we will get a lot of such samples, but the good thing is we learned the peak detection algorithm. So, we will use the peak detection and find, and most importantly this is not f, this is in k, because we are doing FFT. So, we are in k. So, we have to find that value of k where there is a peak, and I call that as k naught. Now, I have found a peak at k naught. So, but I need an estimate of f naught. So, using this formula we can actually map this k naught is corresponding to which value of f naught, considering there is only one sinusoid. Now, this you can repeat with two sinusoid with sufficient spacing, and you try experimenting with different values of frequencies and see how it works. Then add noise, add phase, and check how it works. So, why this is come? Because k naught is for length n up to, because we are doing n point FFT. So, then f naught will be up to a duration Fs. Now, technically this is Fs by 2 and this is n by 2. Why n by 2? Because you get two peaks, one at k and one at n minus k, and similarly f naught can maximum be represented up to Fs by 2, which is the folding frequency. So, this is one example. So, I have a signal in the time domain, and probably this is of I think 50 hertz maybe. So, this is 50 hertz signal, sinusoidal signal, and if I do the FFT, So, this is the frequency plot and this is the magnitude spectra. So, in the magnitude spectra I see that this is the dominant thing, and from this we can estimate the dominant frequency is 50 hertz, and this length of this sequence may be very large, and that is why precisely we got this 50.0, but in practical cases we do not get the exact 50 hertz, we might get some estimate which is close. Why so? I will give you an example, and how this value of n is affecting the spectra or the spectral leakage is evident from this plot. So, if I take n equals to 64, I see there is a peak, but there is all a leakage, and this frequency is spread out in this region. The higher the value of n, so if I increase n, I see this leakage is narrowed down. So, this peak is kind of precise. I increase n further and it is becoming more precise, and 512 point is giving me a very precise frequency. So, for practical purposes, let us try to see an example. So, here we have this signal of 50 hertz and I have a sampling rate of 1000, and 1000 is much greater than 100. So, Nyquist criteria is valid here, and then I am taking 256 samples. Great. So, what should be my frequency resolution, which is Fs by n, which is roughly 3.91 hertz. So, technically if I see, it is corresponding to a k naught value which is 12.8, but k is an integer. So, either the peak will appear at 12 or at 13, and since this is closer to 13, assuming the peak appears at k naught equals to 13. So, what we will get is a peak at k naught 13, which is corresponding to a frequency of 50.78 hertz, and that is why I say this is an estimate f hat, not the exact. Or in other words, I have a sine wave, I do not know where it originates, I just take some window of this in the discrete time domain, I do the FFT, and then from the FFT I find a peak, and from that peak value I remap to the analog frequency and find this estimate which is much close to this. Now, naturally this is very good to find the signal if it is like precision is not a big factor, like if you can always increase this n and get a better precision, but if you are trying to find sinusoids like the broken rotor bar problem, that 50 and 50.5 hertz separately or 50 and 51 hertz separately, this method may not be very good because you might be needing a huge value of n. So, there these other methods like music and esprit will come to the rescue. So, another problem is power spectral density estimation, and this is another very good problem. So, what is power spectral density and what is energy spectral density? So, we already classified signals as power signals and energy signals. So, for power signals we have power spectral density. So, how the power of the signal is for each frequency value, and from this white noise is also defined where we have a flat power spectral density, and similarly for energy signals we have energy spectral densities. So, how do we estimate this? Again I say estimation because we do not have the whole periodic signal, we just get a duration of that, and from that we will estimate. So, this is a 4-step process. First you perform FFT of the signal, then calculate the magnitude spectra, and then you take the square of the magnitude. Now, this is giving you the power, but this is not a normalized PSD. So, you have to divide by n. N is the point FFT you are using or the signal length you can say, and this is giving you the estimate of the PST. Now, for example, if your xn signal is a white noise, you can estimate this PSD and then see the distribution of power over the different frequencies, and if they are almost same, then you can say this is kind of a white noise. And say this is one example. So, this is kind of a sine wave which is corrupted with noise. So, if I do a PSD estimate using FFT, So, we see that although this is very noisy, you can clearly see a peak at some value near 50, and probably this is the significance of this fundamental period of the wave buried with noise to be of a 50 hertz sinusoid. And now this can be improved by methods like averaging periodograms, and there are also advanced methods. So, averaging periodogram is called the Welch method, which is often used in packages like in MATLAB and Python. So, that is it. Thank you very much. We will meet again. Have a nice day.